So let's take a look at this guided practice on strengths of acids and bases. So the first thing we want to do is just describe what's the difference between a strong versus a weak acid or a base. And we're just going to highlight the big important parts first. So if we're talking about strong, either an acid or a base, the idea is that these things, and we'll kind of section this off here, these are going to ionize completely. And what that means is they're going to dissociate or break apart into their ions in solution. So dissociate into ions. And let's just take a look at a couple examples. These also have really high Ka and Kb values. We don't usually evaluate that for strong acids and bases so much, but they're going to have high Ka or Kb values. Okay, so basically what we know is that most everything is going to be in ion form. And so for an acid, let's do an acid first. Here's an example. We could have something like hydrochloric acid, HCl. And when it's in water, it's going to break apart completely into its ions. And so we use just one direction arrow pointing to the products, and we're going to show the hydrogen ion and the chloride ion. Now, I could actually add that with water and show this as hydronium as well. I'm just kind of condensing this down for now. Okay, so for the base, we're going to see something like, say, sodium hydroxide. And it's going to, in aqueous solution, completely break apart into sodium ions, Na+, and hydroxide ions, OH-. Okay. We'll talk about the list of which things are strong here in just a moment. And now, in opposition to that, if we look at the weak ones, so weak acids and bases, these are going to have incomplete ionization, so they're not going to completely dissociate into ions. So incomplete ionization. Okay. These are going to have smaller, in comparison, Ka and Kb values, Ka for acids or Kb for bases. Okay, so let's look at an example. Here's an acid. And I'll give you a specific example for this one. So say we had something like carbonic acid, so H2CO3. And in water, that's going to break apart into hydrogen ions and carbonate. Actually hydrogen carbonate, HCO3. Let me fix that real quick here. Move my plus over there. Okay. And then for a base, the base is really hard to show without including water, so I'll go ahead and include it here, and I'll try to model some of these in additional ways later. So NH3 ammonia is the classic example. Okay, so if we add it to water, and I could have done this with all of the other ones and shown how we got hydronium ions for the acids, the H3O+. Okay. All right, so when this happens, we're going to form an NH4+ and an OH-. And the reason why this is a base is it increases the amount of hydroxide in solution. So let's kind of highlight a couple of the really important parts. So if we're taking a look at the strong over here, notice that these are directional arrows, they only go in one direction, and this is ionizing completely. And then for the weak ones, we have incomplete ionization, and that's really represented by the double arrow forming an equilibrium situation. Okay, so those are kind of some things to look for. Now, a lot of times it's really nice to know the list of which things are strong versus which things are weak. Let me go ahead and see if I can draw this arrow a little bit, or this line a little shorter here. And let's go ahead and write in what our strong bases and our strong acids are. Once you know which ones are strong, then you can kind of, anything else would be on the weak side. So our strong bases, just so you know the list, these are going to be anything that is a metal hydroxide. And so, for example, you could have NaOH, sodium hydroxide. You could have calcium hydroxide, CaOH2, and so on and so forth. Okay, so there's a couple examples. For your strong acids, there's a specific list of them. And this is something you just need to know or remember eventually. So our strong acids are going to be HCl, hydrochloric acid, HBr, hydrobromic acid, and HI, hydroiodic acid. Interestingly enough, those are 3 of the halogens, but hydrofluoric acid is not a strong acid, it's a weak acid. There's reasons for that. Okay. Nitric acid, so HNO3. HNO2 is actually a weak acid. Sulfuric acid, so H2SO4. Those are really the main ones we usually use. There's a couple more here I'm going to add just so you have them on your list. So HClO3 and HClO4. Those are 2 that we don't usually see a lot, but I'll add them on there. So that is the list of strong acids. You just have to know it. So let's take a look at some problem solving and see how we might determine some things. And we're going to use a generic form for this with a weak acid, or just an acid, HX, or we can use HA, however you like to do that. What is the Ka of a 0.2 molar solution of an acid with a pH of 2.0? Okay, so we want to do some problem solving here. The first thing I'm going to do is I'm going to go ahead and set up an ice table. And I like to just write out my generic HX, H plus X minus. Okay. And then I'm going to do I, C, E for initial change and equilibrium. And we know we are starting with this 0.2 molar solution. So I'm going to go ahead and put that value in. 0.200 molar, and that's going to go under the acid. Okay. Initially, we are not going to have any ions. Okay, so when we first put it into water, we're not going to have any ions, and then we want to know what the change is going to be. Now, the change is dependent on the hydrogen ion concentration, so we're going to go over here, and we're going to go, okay, let's find out what our hydrogen ion concentration is. That tells us what the change is going to be. And we know what that's going to be because we have pH. So it's going to be 10 to the negative pH, which is 2. So 10 to the negative second is going to give us 1 times 10 to the negative second, or 0.0100 molar. Okay, do molar here. So we know that there's going to be a change of 0.01. So we're going to take that away from the left side because it's going to transfer from the left to the right as it ionizes. So 0.01, and then we're going to add it to the other side. Now, for every one that we lose on the left, we gain one of each ion, and so we see that there. And then eventually we're going to go ahead and add these up. Okay, so if you like to draw the lines here down, and let's go ahead and add these all up to find out what is going to be at equilibrium. So 0.2, so we can do 0.2 minus 0.01, oops, 0.2 minus 0.01, there we go, gives us 0.19, so 0.190, okay, and then this is going to be 0.01, we can add the extra zeros on there if you want to. All right, so now what we need to do is we need to go ahead and plug this into our equilibrium expression so that we can determine what Ka would be. And so we want to write that expression. We know that our expression is going to be Ka is equal to, and it's always reactants, okay, so the hydrogen ion plus the, times, plus, times the anion over the weak acid, or the acid. If you do have water and hydronium that are on here, you would just have the H3O plus for the hydronium ion. And water doesn't figure into this because liquids are pure substances and they don't go into that equilibrium expression. So now we go ahead and just plug in those numbers that we have. So to solve for Ka, we are going to plug in all of our numbers. So we have 0.01 twice, and so it's going to be the same as 0.0100 squared on the top. Okay, if you'd rather write them out times each other, that's fine. And then all over 0.190, I plug that into my calculator. So let's do that. So 0.01 squared, and then I'm going to divide that by 0.19, and I get this little number here, and so we get 5.3 times 10 to the negative, let's see, 1, 2, 3, 4, to the negative fourth, if I want to write that in scientific notation. Okay, so there is our answer for this problem. Or I can make it sparkly here. Let's make it sparkly. There's our answer. Okay, so let's try this again, but we're going to start with hydrogen ion concentration. And so when we do that, we don't have to do the whole thing of finding the hydrogen ion concentration. We're just given that instead of changing from pH. And so we're going to do the same thing. So go ahead and pause the video and try it yourself here. You can use the same generic. I'm going to actually go ahead and show you this one. So if we were to have it like this, and we showed water, H2O, we would get H3O plus X minus. So I'll just show it that way for fun, in case you like to show it that way better. Okay, so in this case, we're going to start with a 1 molar solution right here. So 1.00 molar. Again, this is a liquid, and so there's nothing that we're going to show for H2O there. It's not part of a concentration. Okay, and these ones start out at 0. All right, our hydrogen ion concentration is already there, and so what we're going to do is we're going to use this. We're going to subtract that from the left side, so 7.2 times 10 to the negative third, and then we're going to add that, so subtract, and then we're going to add it to the other side, so 7.2 times 10 to the negative third plus 7.2 times 10 to the negative third. Okay, we can draw our lines down. Now let's go ahead and add these up just like we did before. So initial plus the change equals what we see at equilibrium. And so in this case we get 0.9 0.928. Do that 1 minus 7.2. I hit the second and the EE button. That's how I like to do that, to the negative third. It works different in different calculators. Oh, I start off with 1 there. Let's do that again. 1 minus 7.2, second EE to the negative third. Just clean that up. Okay, and I get the 0.9928. I'm going to go ahead and keep that whole number so I don't have any rounding issues and it's easy to write. And then, of course, the other two, we're going to see 7.2 times 10 to the negative third. 7.2 times 10 to the negative third. Okay, let's go ahead and plug this into our Ka expression. So I'm going to write the expression again just to make sure. So Ka, in this case, concentration of H3O plus times X minus over the concentration of HX. Okay, let's go ahead and plug those in, those values that we got. So 7.2 times 10 to the negative third, we're going to square that value and divide it by the 0.9928. So 7.2 times 10 to the negative third, I'm going to square that number, and then I'm going to divide it by 0.9928. Okay, and I ended up getting 5.2. Just happens to be close to that other value. So Ka equals 5.2, but in this case it's times 10 to the negative fifth. Okay, so numerical wise it was similar. Okay, so there's our Ka value. All right, let's try something just a little bit further. We're going to start off with a specific example. So in this case, we're given a 0.35 molar solution of boric acid, and if we are given the Ka value, now we're going to go ahead and work through some problem solving. And you can pause this and try it yourself first. I recommend that, and then look back and see where you might need some supports. Okay, so in this particular case, when we get started, we want to just write out the overall equation. Okay, and it tells us here we're going to make this assumption. Assume only one hydrogen is going to ionize. Okay, we'll make that assumption for making this easier, or we're going to just ionize the first one. So here we have our H3BO3. Okay, I'm just going to go ahead and add this with water again like we had in that last example. If you just want to split that apart, you can. That's up to you. Two different ways of doing this. Okay, and on the other side, we're going to get the H2BO3 minus, and then we're going to get H3O plus, that hydronium ion. So just remember, I'm going to write this down here. Remember, H plus is equivalent to H3O plus when we're doing acids and bases. You can do that either way. I think the more proper way is potentially hydronium, but I use them fairly interchangeably. Okay, so the next thing we want to do is go ahead and write our Ka expression. So Ka is going to be the concentration of our ions on the product side, so H2BO3 minus times H3O plus. We're going to divide all of that by only the acid. Remember, water is a liquid. It doesn't go into our expression. So H3BO3. And then in part C, it wants to know what the concentration of hydrogen ions and the pH would be. So we're kind of working this one backwards. So let's go ahead and do that. We're going to set up our ice table like we did before. And so I'm going to scooch my ice table over here just a little bit. So H3BO3 plus H2O. Actually, let's go ahead and do it this way. I'm going to simplify this when I get down here. Again, you can do it either way. Just thinking through that. So H3BO3. Let's go ahead and just pull off one hydrogen, H plus, and then the H2BO3 minus. We'll do that for our IS table. Okay, so what we want to know is what is our hydrogen ion concentration and pH. Okay, we have to go back up to the top to grab some numbers. We need to know that this was a 0.35 molar solution, okay, and we need to know the Ka value. So we're going to bring both of those values down. So the first one is we're going to start with a 0.35 molar solution. And we know we don't have any of these to begin with. The question is how much changed, because we don't already know the hydrogen ion concentration. And so to do this, we're going to have to change by a factor of x. And so we're going to take away x, some value, on the left side, and we're going to add x just like we did before, but we had numbers then. But we don't know what this number is. We're trying to determine what x is. Okay? And so at equilibrium, we are going to have 0.35 minus x, and then we're going to have x and x. Okay? Now, here's what gets tricky. If we keep that 0.35 minus x, our problem solving starts to become a little more complicated because our Ka value is small. Okay? So I'm going to circle this, and I'm going to highlight this for just a moment. And I'm going to say we are going to assume this is negligible. Because we have a small Ka value. And so we can remove it. For the purposes of our class, we can go ahead and do that. When you get to AP Chemistry, we talk about when you can and when you can't do that. So let's go ahead and plug this in to our expression that we already wrote up above. So we're going to do Ka, which we know was 5.8 times 10 to the negative 10th. That's very small. And that is going to be equal to x squared over, and we're just going to make it 0.35. Okay, we're going to make that, this is what we call the 5% rule. Okay, this is something we call the 5% rule. And you can do that on all of these types of problem solvings that you would see for this class this year. Okay, so we want to solve for x, so we're going to move 0.35, so we multiply by both sides. And so we get x squared is equal to 5.8 times 10 to the negative 10th times 0.35. If we want to get x by itself, we have to square root both sides. Okay, and we will find x. So let's do that. 5.8 times 10 to the negative 10th times 0.35, and then I'm just second square root second answer is how I go ahead and do that, and I get 1.4 times 10 to the negative 5th. So x is going to be equal to our concentration of hydrogen ions, and that is equal to 1.4 times 10 to the negative 5th. So there's the first part of our answer. Okay, this is the first part. The second part is we want to know what the pH would be. So since that's our hydrogen ion concentration, we can go ahead and go, oh, well, I know that pH is equal to the negative log of that 1.4 times 10 to the negative 5th. Right, negative log of the hydrogen ion concentration. And I'm going to go ahead and keep that value in that I have on my calculator. And I'm just going to hit the negative button, the log button, and then we're going to go ahead and second answer, get that in there. And we get a pH of 4.85. So a little bit different way of solving that the backwards way. All right, last problem that we're going to try. We want to know what the Kb value is for the conjugate base, okay? And so remember that in this particular case, our conjugate base, so the conjugate base is the H2C, oops, not CO, BO3 minus, okay, that is the conjugate base. And so in order to determine that, what we do for the Kb value, we take Kw, okay, and Kw is a constant. It's always going to be 1 times 10 to the negative 14th. And we're going to divide that by our Ka value. Our Ka value we saw up above was the 5.8 times 10 to the negative 10th. Okay, where we're dealing with the same substances, so that's going to be the value. So we go ahead and plug in those numbers. 1.0 times 10 to the negative 14th. I'm going to divide that by 5.8 times 10 to the negative 10th. Okay, and I get 1.7 times 10 to the negative 5th. All right, we have worked these problems one direction and the other. I hope that is helpful, and we'll do more practice in class.